number known as the base by itself. For example, in the expression 2 to the 3, 2 is multiplied by itself 3 times, resulting in 8. Roots are the inverse operation of exponents, representing the number that produces a given value. When raised to a specific power, for example, the square root of 9 is 3, since 3 squared equals 9. Exponents simplify the representation of large numbers and play a crucial role in scientific notation. They are also vital in understanding exponential growth and decay in real-world scenarios, such as population growth and radioactive decay. Roots are important to solving polynomial equations and are used in various fields, including engineering and physics. Understanding roots aids in simplifying expressions and finding solutions to problems involving squares and higher powers. Exponents and roots form the basis for higher-level mathematical concepts and functions, including logarithms and complex numbers. Mastery of these concepts is essential for advancing in mathematics and related disciplines. When multiplying two expressions with the same base, add their exponents. For example, a to the m times a to the n equals a to the bracket m plus n bracket. This rule streamlines calculations, making it easier to compute powers quickly. When dividing two expressions with the same base, subtract the exponent of the denominator from the exponent of the numerator. For example, a to the m divided by a to the n equals a to the bracket a minus n bracket. A to the bracket m minus n bracket, simplifying division of powers significantly. To raise a power to another power, multiply the exponents. For instance, bracket a to the m bracket to the n equals a to the bracket m times n bracket. This property is useful for simplifying expressions and performing calculations efficiently. Any non-zero base raised to the power of 0 equals 1. For example, a to the 0 equals 1. This rule is essential in mathematics for simplifying expressions and handling limits. A negative exponent indicates the reciprocal of the base raised to the absolute value of the exponent. For instance, a to the bracket minus n bracket equals 1 divided by a to the n. Understanding this rule is crucial for simplifying complex expressions involving negatives. Radical expressions can be simplified by reducing the number under the square root and factoring out perfect squares. For example, square root of 50 can be simplified to 5 times square root of 2, as 50 equals 25 times 2, and square root of 25 equals 5. The product property states that square root of a product is a product of square roots. For instance, square root of bracket a times b bracket equals square root of a times square root of b. This property holds for any non-negative numbers a and b. According to the quotient property, the square root of the quotient is the quotient of the square roots, expressed as square root of bracket a divided by b bracket equals square root of a divided by square root of b. This is applicable for non-negative a and b, ensuring the denominator is not 0. Rationalizing a denominator involves eliminating roots from the denominator fraction. This is achieved by multiplying the numerator and denominator by a suitable root. For example, to rationalize 1 divided by square root of 2, multiply by square root of 2, to obtain square root of 2 divided by 2. So you multiply the top and bottom by square root of 2. The base in an exponential equation is a number that is raised to a power. For example, in the equation 2 to the x equals 8, the base is 2. Identifying the base allows for effective manipulation and simplification of equations. To solve equations with the same base, set the exponents equal to each other. For instance, 3 to the x equals 3 to the 4. X must equal 4. This method streamlines finding solutions efficiently and accurately. Logarithms can be used to solve exponential equations when bases are not the same by applying the logarithmic identity. Log base b a equals c. We can rewrite the exponential equation in solvable form, such as log of 8 divided by log of 2 equals x. Exponential equations appear in calculating compound interest, population growth, and radioactive decay. For example, the formula a equals p times bracket 1 plus r divided by n bracket to exponent n. T models compound interest over time, showcasing practical uses of exponential relationships. To solve a radical equation, begin by isolating the radical on one side of the equation. This simplifies calculations and enables the effective squaring of both sides to eliminate the root. Once the radical is isolated, square both sides of the equation and remove the radical. This step is crucial as it transforms the radical equation into standard polynomial equation. Post-solving is essential to check for extraneous solutions by substituting potential solutions back into the original equation. This ensures that the found solutions are valid and not results of the squaring process. Radical equations frequently appear in various fields like physics and engineering. For instance, finding the length of a side of a triangle or measuring distances requires solving radical equations to obtain precise answers.